All right, I'm going to do this with, let's use just a DC type current. All right, let's just use a DC type current. Hold on a second. I got to pause you. Now, how do I do this? I hit escape, alt option. Okay, now I got you back. See, when I do that, then I've got this up here in the corner, so then I can do this, and then I'll be able to, it's taken me 3 years to figure that out. All right, well, here's the problem. Let's go ahead and magnify this a little bit so you can see it. Here's a problem. This is a good one. Okay. So here's the problem. It says the starting current in a DC motor. Okay, so we're not looking we're not looking at a AC motor. I found that diagram. I mean, it was okay. It was okay, and it was true, and it was good. But if we just go if we just use DC, we can draw this a lot easier. So a starting current in a DC motor is 20 amps. Okay, so that's starting current. So let's just write down IS. It's equal to 20 amps. Okay? And this is, but it normally operates at 110 volts. Okay? So the operating voltage is equal to 110. That's to get it started. But it has a back EMF, E of 90 volts. All right, so here's what the diagram looks like. First of all, what's the resistance in the windings of the motor? Okay, remember, resistance does not change. And then we're going to look at what is the current at normal load. What's the resistance? R, constant. It doesn't change unless it gets hot. Heats way up. Then the resistance will go up a little bit, and the voltage will drop, and the current will drop, and then eventually, if it gets too hot, it burns up. And then everything stops. Okay, but anyway, so R is constant. It's got an operating voltage of. Here's what's going on. When you first turn it on, R looks like this, or the circuit looks like this. First turn on. First turned on. First turn on. I won't talk about when that happened, but anyway, first turned on. Here we go. When were you first? Anyway, oh man, sorry. Friday. 110 volts. Got R here. When it's first turned on, its starting current, IS, is equal to 20. Oh! IS. Why did I say AS? Because I was thinking of amperage. Is equal to 20 amps. IS is equal to 20. Well, I wonder what the resistance is. V equals IR. 110 over 20. What is that, 5.5, something like that? I don't have my, oh, I got to use this crappy Casio calculator. I hate this calculator. 110 divided by 20. Boom, 5.5 ohms. 5.5 ohms. Now, R stays the same throughout the problem. But here's what happens. Now it's been running. Starts running. Starts running. This is also why, before I get any further, when you turn it on, I've got a huge current. This is also why when you plug in your hairdryer at Grandma's farmhouse or in your old apartment down, you know, at oh, I don't know, down by Troost, you know, where some of you live, you know, between Rock Hill and Troost, one of those older homes. Boom, the fuse blows because you're getting too much amperage going through there. Can't handle it. But when it's, and if you've ever noticed when it's been running a while, you don't blow a fuse. Now, if your friend plugs something else in, that might blow a fuse. If it's not wired, if it's wired, especially if it's wired in series, that could be a bad thing. All right, but anyway, so now it starts running, and it's running for a while. Okay, running or operating. Now it's running or operating. So here we go. So now what happens is you got a current. Look at this. We got a current going through here. This guy is pushing a current going this way. This starting current's going through this. And so it's going to go through there. And this voltage drop here when you first turn it on is going to be 110 volts. But now when it starts operating, this current actually drops because it's creating a magnetic field in there. It's creating a magnetic field in there that will also induce an EMF that's going to oppose the change. Okay? So on this one, doing right-hand rule number 2, doing right-hand rule number 2 on this one, where, remember, there's right-hand rule number 2. Put that here. So I've got this magnetic field going in here. It's being created in here. Well, that's going to create a back EMF that's going to be opposite this guy. So when it starts operating, when this happens, here's what goes on. I probably should have been drawing it down here. Got 110. Now, look at how I drew this. Now I've got 90 going the other way. So it's going to start pushing charge this way. Got a current going like this. This is the operating current, which I don't know. The operating current, I don't know. But I've got a charge going this way at 110. Pushing that current that way. But this guy's going, whoa, I want to push current this way. I want to induce a current going this way. Because why? Because this guy's causing the current to go in. And I want a current, and I'm here to induce a current that's coming out. So I want to induce a current going this way. All right? I can't do that because you're overpowered. You're bigger than I am. So what's the net voltage? V minus E, which is the back EMF, is equal to 90, or 110 minus 90, which equals 20 volts. Okay? So now what's the operate? So when it's operating at normal load, what's the current at normal load? Normal load is another phrase for operating current. Okay? Current at normal load, piece of cake. I've got 20 volts is equal to I operating times R. Remember, R hasn't changed. We've already solved for R. So I've got 20 divided by 5.5 is equal to I naught, which is equal to 3.6 amps. Piece of cake. Piece of cake. So the actual formal equation for this is the back EMF. The back EMF is equal to the voltage that's in your battery, or your DC, or even your AC, your AC, your normal, the root mean square of your AC voltage is equal to your voltage, okay, in the battery, minus I naught times R, where I is the operating. Okay? But to find I starting, notice the R. So if I'd have given you R, and if you'd have known what the resistance was, we could have just jumped straight to finding the operating current. But so this is the equation for it. But we have to know we have to either know the resistance or the operating current. And the way we find the resistance was we look at the starting, when it's first starting. And so it's operating at 110 volts, but also its voltage when it first starts is also at 110. Starting and operating this way. But the operating voltage gets changed, but there's the battery or the outlet is going to be 110, but it's going to create this back EMF due to, why? Conservation of energy. There you go.